Welcome to this presentation on analyzing variables for 90-day functional outcome prediction of endovascular thrombectomy. This work was done in collaboration with 5 research groups in the area of Erlangen, Germany, and it is part of a project funded by the Bayern Innovative Agency. To begin, I will explain the two main concepts related to the topic. The first is endovascular thrombectomy, or EVT, and it is the gold standard treatment for acute ischemic stroke, which accounts for over 70% of the strokes. This procedure is minimally invasive and aims to remove the clot that causes the ischemic stroke. The second key concept is the functional outcome, and it is often measured using the modified ranking scale that measures the degree of disability. A score of 2 or less indicates a favorable outcome, and it means that the patient can carry out daily activities independently. The general aim of this research is to use different variables to predict functional outcomes, and from the outcomes, analyze the variable contributions to the predictions. We can make predictions before and after the thrombectomy. Before the thrombectomy, we use 34 variables extracted from patient data, clinical data, and image data. The image data was extracted from CT scans. We want to predict whether it is worth performing the thrombectomy in accordance with the expected functional outcome. After the thrombectomy, 13 variables were added. They were extracted during the EVT and from a follow-up CT scan performed 24 hours after the procedure. Here, the idea is to predict the expected functional outcome 90 days after the thrombectomy. Related works commonly utilize decision tree ensembles and artificial neural network for predictions. However, these methods are not naturally suited for variable analysis and often require additional techniques. Tree ensembles, in particular, can be biased towards variables with high cardinality, necessitating careful handling. For variable analysis, other studies frequently employ logistic or linear regression, and occasionally they use ANOVA when dealing exclusively with categorical variables. While these methods offer interpretability, they often result in lower prediction accuracy compared to more complex models. We propose using ForestNets to make a unified prediction and analysis. ForestNets is a nonlinear method that combines the predictive power of neural networks with the interpretability of decision trees. This method allows us to map an ensemble of decision trees to a partially connected neural network. Once the network is trained, it is used for predictions, and because its architecture resembles the trees, it is also used for variable analysis. In this example, this tree ensemble is used to build this neural network. The tree on the left has 4 branches, and therefore these 4 hidden neurons. This tree on the right has 3 branches, and therefore 3 hidden neurons. Only the features involved in the branches are connected to the respective hidden neuron. We can also see that the higher a variable is in the hierarchy of the trees, the more connection to the hidden neurons. For example, X6 is higher in the hierarchy and it has more connections than XN, that is lower in the hierarchy, that it has only one connection. And that's how we can measure the contributions of the variables to the predictions, depending on the number of connections to the hidden neurons. For the experiments, we performed a retrospective review of 268 patients treated with EVT from 2015 to 2019. To build the neural network, we used a gradient boost tree assemble with 5 trees. And once the network was built, we used binary cross-entropy loss to train it with an Adam optimizer. We used a 10-fold cross-validation approach 10 times, and the final prediction was the average of those 10 times. To measure the performance, we estimated the drop curve and the AUC, and once the operating point was fixed, we estimated the specificity and sensitivity, and finally the accuracy. Here are the ForestNet prediction results. Before EVT, an AUC of 82 is achieved, that it is reasonably good. However, the additional 4 points gained on the predictions after EVT are not neglectable. Regarding the metrics estimated after fixing the operating point, all metrics show an increase of 2 to 3 points after EVT compared to those before EVT. Here we can see the ForestNet variable analysis. Although we only show the top 5 variable contributions for space constraints, a full list can be seen in our article in the proceedings. Before EVT, the top 2 are highlighted in red. Their distributions in accordance with the outcome are here. We can see that there are large areas without overlap. After EVT, we also highlighted the top 2 contributions, but excluded those repeated in the top 5 before EVT. We can see that there are also large areas that do not overlap in their distributions. To wrap up this presentation, we can confirm that ForestNet effectively predicts 90-day functional outcomes. It also provides detailed variable analysis, and this implies that healthcare providers can utilize these predictions and analysis to enhance treatment planning and deliver more personalized care. More generally, this work showed the capabilities of ForestNet to provide a unified solution to outcome prediction and variable analysis. In future work, we aim to analyze further the similarities between the assemble of decision trees and the built ForestNets to extract additional information, such as decision thresholds. This might help to elaborate EVT recommendation guidelines. With this, I conclude this presentation. And now, I would like to thank you for your attention and invite you to read our article for additional results and a more detailed analysis of the variables.